Welcome everyone to this afternoon session on machine learning in low value care, the promises and the pitfalls. I'm Dr. Joanna Lawrence, a paediatrician at the Royal Children's Hospital in Melbourne, and I'm delighted to be chairing what promises to be a fascinating discussion examining how machine learning might help us reduce unnecessary or wasteful care. Firstly, to acknowledge country. We extend our respect to all Aboriginal and Torres Strait Islander and Māori people, including those present today, and value the importance of their ongoing connection to land, sea, sky, and community. We pay our deepest respect to elders past, present, and emerging, and together we restate our shared commitment to advancing Aboriginal, Torres Strait Islander, and Māori health and education as core business of the college. All right, today we're talking about the opportunities arising from machine learning, which for those of you in the audience as non-techie as me, is essentially using computers to analyse large data sets, for example, the ones we're all generating through our electronic medical records, to identify patterns that the human brain cannot detect. And in the context of low value care, using these patterns to alter our pre-test probability, so we know which tests are likely to provide new and valuable information and which we can avoid that will add little benefit. And for those of you who have been working to try and reduce low value care, you will understand the limitations of tools like education, audit and feedback, guidelines. So is machine learning the answer? Well, I'm looking forward to hearing what our speakers have to say. Just before we do so, can I draw your attention to a paper which we'll be referring to in the session today, which you can access and download in the right-hand panel of your screen under the tab Handouts, if you'd like to refer to that. And now let me introduce you to Professor Ian Scott. Ian is the Director of Internal Medicine and Clinical Epidemiology at Princess Alexandra Hospital in Brisbane and Professor of Medicine at the University of Queensland. He has been a clinical lead in hospital digital transformation since 2015 and chairs the Metro South Health Clinical AI Working Group, which is developing and validating machine learning applications in medication prescribing, risk profiling, and image interpretation. He has authored several publications in the field of AI and is a member of the RACP Digital Health Advisory Group. Thank you, Ian.
Thanks very much, Joanna, and welcome everyone. And I think this is going to be a very interesting session. I very much look forward to the talk from our international speaker. So today what I thought I'd do is just give a bit of an overview of machine learning, what it is and perhaps what it isn't. And also then talk about what are some of the promising applications that machine learning is now looking at, what the actual machine learning pipeline is, but also perhaps consider some failures and limitations and things that we need to be careful about. And in that, perhaps look at a checklist that we've developed recently, trying to help clinicians and data scientists and others assess the suitability of machine learning applications for clinical care, and then perhaps talk about where to from here. So as Joanna mentions, what is machine learning? Well, it's basically taking advanced computer programs, they're the machines, and then processing these huge data sets that we have now available to us and using those to iteratively train and refine or learn a layered model or algorithm, which when we apply it into new data, hopefully yields an accurate prediction or an outcome. And under machine learning, we now talk about deep learning, which is a subset whereby we apply multi-layered neural networks to large data sets to perform very complicated tasks, such as speech or image recognition, and where the algorithms actually, the software itself, learns to train itself to perform tasks. So people ask me, well, Ian, do we need this? What's driving this sudden interest in machine learning? And I think, well, we all need to understand and appreciate that in modern healthcare, it's a very costly business. We're trying to be more precise in the care that we give to individual patients, trying to maximize benefit and also avoid low value care, in particular, trying to prevent patient harm. But we also want to reduce waste and inefficiencies because we consume a fair percentage of gross domestic product and it's growing. And is it sustainable over the long term, particularly when we're told that up to 30% of the expenditure on healthcare is actually wasted and not particularly beneficial. But also we have to think about eliminating care inequities. And certainly in Australia, we have a big gap between our Indigenous health indicators and those of non-Indigenous folks. So we need to make sure that that gap is closed. So in doing this, and in actually achieving these aims, I think we need a couple of things. Well, first of all, we need for speed. I think one of the most limited resources that clinicians have in the modern age is time. Time to actually spend talking to their patients, interacting with patients, rather than interacting with computers or doing mundane things that could be automated, or being distracted often by false alerts and other things. And that is very difficult then to allow one to keep track on what you're doing and what you're actually talking to patients about. We also have cognitive biases. I think we all have to admit that we're human, we're fallible, and we all have hidden biases in the way we make decisions, which often is due to our prior training, or maybe that fears, medical legal concerns, and other things drive us to do things which we know, perhaps in our heart, that perhaps this is not the best thing to do. Humans also are not particularly good at multitasking. The human mind can probably only process about 6 or 7 things simultaneously, but we know that computers can do this very much better, and therefore can process a number of functions simultaneously. We have limited short-term memory, whereas computers can hold terrific amounts of data and process it and keep it and store it and reuse it. We are distractible and fatigable because, again, we're human. We're not robots. We're not machines that can then just continue doing multiple tasks without fatiguing. And also, we have to acknowledge that knowledge continues to exponentially grow, and it's impossible for anyone, even in a very narrow specialty, to master all known knowledge. So again, can machine learning help us deal with this information overload? There's no doubt there's a growing clinical interest in machine learning. It's interesting over the last few years how across a number of different disciplines, people are now starting to take an interest, trying to inform and educate everyday clinicians as to what machine learning is and how it can perhaps be useful, and also talking about what are some of the developments and applications that are now coming on stream. In Australia, we are starting to, I think, spend a reasonable amount of research money, $19 million federal government expenditure in 2020, and it's probably going to be twice that, if not more, in 2021. So we are now starting to consider how we can apply machine learning in looking at things that are common, that pose concerns in relation to screening and diagnosis, or perhaps even in terms of management. And when you look across the globe, there's now hundreds of machine learning applications that have now received regulatory approval in the USA or across Europe. And in Australia, though, we're perhaps lagging a little behind because looking at the therapeutics goods administration approvals, there's only 2 that have actually been registered as of yet. So perhaps is this because we're cautious, more cautious in Australia, or perhaps do we feel that we don't necessarily have the data systems to actually cope with some of these new applications? So just to briefly, just to give the uninitiated a bit of an overview of machine learning methods, and there's basically 3 types: supervised, unsupervised, and reinforcement. And today we're going to be talking about supervised learning, in particular classification. In other words, using machine learning to be able to diagnose or to be able to determine whether an outcome or a prediction is basically a yes or no type question. So does the patient going to die or not going to die? Is this result going to be abnormal? Is it going to be normal? Is this the diagnosis or is it not? Unsupervised learning doesn't require known outcomes. It actually looks at data and tries to recognize patterns and latent similarities between different groups of features in a data set. Whereas supervised learning, we know what the outcome is. And what we're trying to do is train the model to actually predict that outcome accurately. Reinforcement learning, I think, is obviously in its infancy and is more dynamic and looks at reward trial and error type learning and is particularly suitable for dynamic situations such as intensive care. But it's still, I think, a way yet to any level of maturity. So where we have most of the advances at the moment is in supervised learning, and in particular classification. And I just mentioned this article that's now online that in that I hope to demystify machine learning for the non-statistician. So please have a look. Now, there's whole heaps of machine learning models, and they just continue to grow and grow and grow. In supervised learning, these are the more common types that you may hear the names of. I'm not here to give you a detailed explanation of each of them. It's not easy necessarily to explain, but just to sort of indicate that these terms you'll hear in relation to supervised learning. We also have now deep learning, and in particular, convolutional neural networks for imaging data are probably the most well-known. but we also have recurrent neural networks and generative adversarial networks as well now coming on stream. And finally, we have ensemble learning, where we don't look at perhaps just one model, we actually aggregate different models and actually try to find the best one or the best combination of models. So basically, any machine learning pipeline consists of these basic components. We have a data set of input data. Often that data set is then split into a training set and to what we call a holdout or validation set. And there may be, in some cases, a tuning set that's more intermediate. So the model is actually developed and then tested in silico using this training and holdout sample. And then the model should be subjected to what we call external validation. In other words, it goes outside its immediate training environment and is tested on a new data set that the model hasn't previously encountered. And in that way, we test whether it's robust and can actually be generalizable. And many different models can be tested simultaneously within this training set. And as I said, often ensemble methods are used to provide the best model. So we have this model pipeline. So the first mile is basically capturing the data, cleaning it, and labeling it. The middle mile is then building the model and testing it. But the last mile, and probably one of the most daunting challenges yet, and perhaps one that's still hard to pass, and that is real-world implementation and routine use. So we have the development and validation phase, as I said, which is sort of basically a desktop exercise, but then the production phase is when it's actually turned into a real-world application. And we need to make this very important point that models can perform very well on the desktop, but don't necessarily equate to then clinical utility when we try to translate it into clinical practice. And we need to also realize that a good percentage of data science and machine learning projects have actually failed when they come to real world implementation. So this is, I think, a big challenge. And I think just expanding on this a bit more, that the first mile, and I've given this figure in terms of the arrows, the length and the strength of the arrows indicate the amount of effort that needs to go in. So often the first mile can be quite daunting in actually collecting the data, bringing it together from different repositories, processing it, labeling it, using expert clinicians. That can be a big challenge, particularly for data scientists who are working in the absence of clinician engagement. And then we have the model validation, model development and validation in the second mile. And that's perhaps not, that's rather easier to done. The software can do it very quickly once you've got the data set. And then you have to validate externally, and that takes a little more time as well, particularly with multiple sites. And then, as I said, the third mile is the difficult part, where we have to then put this into some sort of tool, have an interface that clinicians can use. Do they like it? Can they use it? And then test the tool in terms of silent mode to make sure that it is actually producing accurate outcomes and that clinicians feel that it's not producing counterintuitive results. And then doing a more effectiveness trial where it's in active mode, and we do a before and after, or perhaps even a randomized controlled trial, then to determine is it safe and fully and as effective as we would like. And that's the third mile, and that's the challenge for us all. Having said that, though, in terms of diagnosing conditions, particularly in relation to imaging data, where really we have, I think now, got a number of applications which have been through randomized controlled trials and show performance that's probably equal, if not better, than specialists. So I've listed some of them there, and they continue to grow. And as you can see, they cover a number of different disciplines. And as I said, have received regulatory approval. Diabetic retinopathy was one of the first cabs off the rank, where we now have a camera that incorporates software that can diagnose diabetic retinopathy. And this is a big advance, particularly in isolated populations where you don't have ready access to ophthalmologists. And I think that one of the big advantages or potential gains from machine learning is that it democratizes access to specialist expertise. And I think that's a good thing. We can also use machine learning to estimate disease risk and prognosis. So there again, there's some additional models that look at, for example, trying to predict cardiovascular risk in asymptomatic patients, who's going to die from septic shock, who perhaps may have a leak after their colorectal surgery, what the neurological outcomes may be following head injury, and who's at risk of developing recurrent breast cancer. We also have machine learning models that can predict treatment response, and this is useful. So, for example, in HIV patients, which could, there are a number of different possibilities and combinations of drugs, which one is particularly good for a particular patient. In Parkinson's disease, again, we have multiple options. What's the best selection there? Patients with major depression often have multiple trial and error with 6 or 7 antidepressants before they find the right one for them. In breast cancer, what's the role of neoadjuvant chemotherapy? and in patients with end-stage renal disease, which erythropoietic agents are best to control their anemia. I think also more recently, we've seen machine learning really produce some rather new information as to new disease phenotypes that we weren't currently aware of. Often, particularly in young infants and young children, we've now, I think, got a better idea of rare diseases that we previously didn't understand, and now we're modeling their phenotypes and integrating that with genetic evidence. And then more recently, we've had in various diseases, such as rheumatoid arthritis, hematological malignancies, and sepsis, we're starting to differentiate different subtypes of diseases, which also then respond differently to treatments. And in the figure that I'm currently showing you in relation to sepsis, we've been, folk have been able to identify 4 different types of sepsis phenotypes, which have varying mortality and which also have varying response to different therapies. This, I think, is exciting because it's now actually allowing us to be more predictive as to which patients are going to respond to which therapy. I think also assisting drug and vaccine discovery. I mean, machine learning has played a role in COVID-19 in helping us repurpose existing drugs, which are then subject to clinical trials, looking at new synergistic drug combinations for anti-cancer treatments in particular, and modeling protein conformations, which now take machine learning literally minutes to weeks to do, whereas before it used to take us months, perhaps even years. It's assisting us in education and research in terms of updating research databases and systematic reviews. We can now produce rapid reviews literally within weeks, whereas often in the past it would have taken months to produce a systematic review, optimizing literature search for comparative effectiveness studies, even assessing physician competence, and selecting eligible patients for enrollment into clinical trials. And operational efficiency and safety. So how can we better triage, schedule appointments, improve clinical workflows, particularly in radiology, producing problem lists from EMRs, even using AI-driven digital scribes, which I'm sure my residents would love rather than have to copy notes themselves. Compiling relevant medical literature in response to clinical queries, detecting medication errors, and as we'll hear today, perhaps avoiding unnecessary investigations as well. But there have been some failures, and I think it's important that we recognise that there have been some instances where, in fact, the machine learning model got it wrong, and if we had used it in routine practice, we may have done some real harm. And I won't go through those line by line, but simply just to give you an idea that we need to be careful. We need to validate these models. We need to make sure that in different environments, they produce the same level of performance, and that the model has actually been trained and it's been specified in terms of the task it's supposed to do. So there are limitations in machine learning. I think we need to understand that most machine learning applications at the moment can only perform narrowly defined, mostly binary, that is yes, no tasks. Machine learning, I think it's important that we realize that it's unable to make causal inferences. So it recognizes patterns, it has correlations and associations, but that doesn't actually mean cause and effect. It can't really abstract reasoning. So for example, when the apple falls from the tree, machine learning can work out the mass, the velocity, etc. But it took Isaac Newton to actually conceive the concept of gravity. And also it's hard to explain. In many cases, particularly with deep learning, it's a bit of a black box. And I think that's going to be a challenge for us to make these types of applications explainable. And importantly, I think machine learning, because we can apply it across a large number of digital platforms, it can certainly amplify bias and error at scale. And I think that's why people have a concern and really want to make sure that machine learning is up to scratch. So in helping us decide, okay, when should we use a machine learning application? This is a checklist that my colleagues and I, Stacey Carter and Enrico Chiera, put together and published a little while ago. And I'd just like to take you through the questions on that checklist. So the first question is, what is the purpose and the context of the application? And this has to be driven by a clinical need. And I think data scientists sometimes have gone a little bit carried away and said, we've got some data, what can we do with it? Whereas what we really should be asking, what's the task that the clinicians wants this application to solve or to help them with? And for that reason, I think developers need to collaborate with clinicians. And that's why we as clinicians, as physicians, we need to understand machine learning if we're going to engage in this task. So what is the problem this application is trying to solve? So we need to understand, well, who are the participants and where's the setting and what behaviors are we trying to change? Is the problem amenable to machine learning? Because in some cases, it's not. It may be a task that is really not automated. We really can't automate it. It requires far too much subjective interpretation. It may be that high quality data isn't readily available or accessible at the point that the application has to actually have that data available. Can we actually embed it in existing software? Is it going to stand alone as a standalone app, for example? So we need to sort of think about how easy is this going to be, right, in relation to producing a product that clinicians can actually use. And clinicians will say, how accurate is this model? So we have to ask, well, how accurate must the model be to be clinically useful? It doesn't have to be 100% perfect, but it needs to be at least as good as the current human system, if not better. And that often then raises the biggest question, well, what are we most worried about in relation to the predictions of this model, the false positives or the false negatives? And that really comes down to the actual clinical scenario that we're talking about. How should the model outputs be best presented, interpreted, and used by clinicians? Because we can have a range of different displays and formats, but clinicians don't have a lot of time. They want to be able to understand this quickly and be able to action it. And that then brings the final question, how explainable does the model need to be? Because clinicians, by and large, they like to understand what's underneath the bonnet, and they don't necessarily want to just take on face value something that they have no understanding of. So next question is, how good were the data used to train the model? And we have to ask the data, is it accurate? But more importantly, is it free of bias? So I think we're all familiar with the aphorism, garbage in equals garbage out. So the data has to be accurate and complete, and it has to be properly labeled, and it has to be representative, and hopefully derived from reasonably reliable sources. So laboratory data is pretty good. Clinical registries and trial data sets are also pretty good. What's written in an electronic medical record or what's coded in admin data sets may be a little more soft in terms of the accuracy. Importantly, though, it's bias in equals bias out. And that's why there's a lot of focus on machine learning at the moment. How can we actually minimize bias in the way that the model is trained? So we have to ask, well, what data was collected, how was it collected, and on whom was it collected? So things that may be very important in our predictions, such as race and gender and language and socioeconomic status and other things that we as clinicians kind of take into account, we integrate that in our decision-making, may not be readily captured in many data sets. The algorithms can learn and automate and accentuate existing biases. So we may have a bias in the sense that, well, in the case, for example, of Indigenous folk who only comprise about 3 or 4% of the population, if they're not adequately sampled, then any prediction model that we make that doesn't have adequate numbers of those patients in the training set, well, then clearly it's not going to apply to them. We may also have insufficient data. So we sample them, but the data that we actually collect from them in relation to the factors I've just mentioned above, again, may not be complete. And we have outcome noise, where the omitted variables then may influence model predictions, things that we don't know about, or perhaps we're aware of, but we just can't capture them. So when models are being developed, they need to actually look at what strategies we use to mitigate these various biases. How good, again, were the data used to train the model? Question 2B is, were the data labeled correctly? So in the case of objective data, such as pathology results with reference ranges, well, they're pretty good as reference standards because you can't sort of mess around with an automatic analyzer. It'll spit out the result and the reference range is pretty well established. But where there's subjective interpretation, for example, labeling a retinal image showing diabetic retinopathy or an ECG showing atrial fibrillation, that requires the subjective judgment of a panel of experts, be they ophthalmologists or cardiologists. And we therefore need to make sure that were those panelists, were there a sufficient number of them, were they blind to the model predictions, and were they given sufficient time information to make a considered decision? And finally, under question 2 is, were the data standardized and interoperable? So in other words, we may be wanting to get data and making predictions from a whole range of different sources, from EMR, from laboratory data sets, from imaging data sets, even perhaps from genomic data, proteomic data. All these data sets are in different formats, and the algorithm that's been developed often will be trained to expect information to come in a certain way, in a common data format. So if you go to one hospital, they may do things a little differently, code a little differently. Perhaps the settings within their instruments also are different. So there needs to be this ability to combine this data and put it into a common data format. And that also then is a challenge for bringing data together from a range of different sources. There's things that can help, and certainly standardized structured data that is well coded is not a problem. Imaging data is not a problem because that's subject to a standard, but if we're looking at unstructured text in medical records, that can be more of an issue, although there is now natural language processing models that are now starting to map words to clinical concepts. Was there sufficient data to train the model? And basically, there's no real, at this stage, agreed universal standard for determining the required sample size. And simply, rule of thumb, more complex the model, more differentiations it must make, the more data really you will require. And if more data continues to improve the performance, then okay, we should try to provide more data. There's various techniques that have been used to try to account for things like missing data or what we call highly dimensional data in relation to imaging, which I won't go into. But nevertheless, these methods are certainly helpful, but I think we need to bear in mind that there's only a certain amount that you can adjust for missing data or highly unstructured data. Question 4, how well does the model perform? If we're talking about yes, no, or basic binary tasks, then we talk about this model here, which I'm sure people will be familiar with in terms of the correlation matrix, or confusion matrix it's called actually in machine learning, about true positives, the false negatives, and the true negatives. There's a little bit of change of terminology. So for example, in machine learning, precision refers to positive predictive value, okay, and recall refers to sensitivity, just so that you don't get confused by those two terms. Basically, there's two types of validation, as I mentioned: internal, using the actual data that you train the model on, and that requires different forms of sampling, bootstrapping, or cross-validation, which I'm sure John can talk to more about, and external validation on unseen data. And then we need to also work out, okay, in terms of the decision threshold, because we're making a prediction in terms of whether whether an outcome is present or absent, or whether a result is normal or abnormal. And in that, we have to then decide, okay, where we're going to actually set that threshold in terms of sensitivity and specificity. So often we want highly sensitive thresholds that give a high negative predictive value if the false negatives are the bad things that we want to avoid. Or alternatively, we want highly specific threshold with high positive predictive value if the false positives are the things that we need to try to avoid. And just introduce the concept of fitting. So we have models that can be underfit, overfit, or just right. And the point of this is that we have here we have two features, feature 1 and feature 2. So we're trying to distinguish between these two. We're trying to make a plane of separation. And you can see that this model kind of underfits. There's quite a few features it doesn't actually group, whereas this model really gets everything. But of course, the problem here is that when you apply it then to unseen data, it's probably going to overfit. In other words, it's going to produce a lot of variance because it's tried to include everything. And what you want is the balance here in the middle, where you have most of the features separated, but there is a little bit of overlap. No model is going to be perfect. You always have this balance between what we call bias and variance. And the idea is to try to balance the two. On the right-hand side, we see what we commonly report as receiver operating characteristic curves and precision recall curves. And we can set that decision threshold, that red line, to the left or to the right, according to what we think is most important in terms of false positives and false negatives. A big challenge in terms of machine learning is class imbalance, where what you're trying to predict, say, for example, a rare disease, the problem is it is rare, and therefore you don't have many examples to work with. If you have more examples, then the model can train and learn much easier. Is the model transferable to new clinical settings? And I think, again, important because, okay, if you produce a model in 1 or 2 or 3 hospitals that perhaps may be very similar, but then you go out to a regional hospital, you perhaps even go out into a primary care setting, then of course things may not then work quite as well. And most studies would show that as models are then transferred to new settings, they tend to underperform, their performance goes down. And why is that? Well, because you have differences then in the population that you're dealing with. So the disease prevalence may be different, or the severity may be different, or the way that for example, an imaging device, the type and reporting formats may be different, or it may be that the care protocols or the standards of care within that institution are different systematically from another hospital, or perhaps the data isn't of good quality, or how people actually code the outcome is different. So these things have to be sort of considered. Question 6, are the model outputs clinically intelligible? And there's 2 aspects to this. Is the outputs interpretable by clinicians? And does also the model indicate its level of confidence in its predictions? Because models can, aren't going to say they're 100% confident. They will actually produce a score which may be from, say, 1 to 100. 100% certain, 0 not so certain. And here's an example of a format in relation to looking at skin lesions, where this is the pattern that the computer generates and then translates into an output that the clinician then can decide which one of these they want to use. So this gives a probability of different types of skin condition, whether it's just simply malignant or non-malignant, or it gives a color code, and it's up to the clinician then to match it with what they think is the most appropriate color in determining the actual lesion, or in some cases, even crowdsource, take it out to multiple people and they can then make a crowdsourced decision. Interestingly, in this study, the format that the clinicians preferred was panel 1, giving us a probability of each of these different types of lesions. The second thing under the our model's outputs clinically intelligible is explainability. So how were these predictions derived? And here we're talking about the concept of feature importance. So which of the many features, and in some models they may have hundreds of features, which of these features were probably most important in determining how the model decided what it's decided? And there's different sort of software programs now that can be applied to machine learning models to help distill out those features. And that just gives the clinician a little more reassurance, a little more understanding of why the model has produced the prediction it has. In terms of both imaging data, where often you use what we call heat maps to show the areas in the image that seem to be particularly important in pathogenesis, or in terms of convolution maps, where we look at the actual features and their strength that would determine whether, for example, in this particular case, the model predicted diagnosis of COVID or not. The thing is that we have this explainability performance conundrum. So the more complicated the model and the more highly performing it is, it's going to be more difficult to explain it to a clinician. But I think if we can look at feature importance and try to distill out those features that are most relevant, that at least I think gives some reassurance. Number 7, how will this model integrate into workflows? So if clinicians are to use it, it's got to be safe and accurate, quick and easy to use, provide real-time decision support, preferably self-activates in response to specific requests. So the clinician doesn't have to actually work out, I'm going to turn this on now. It actually does it itself. The data that's inputted into the model, it does that automatically. So again, we don't have to punch information in. It's there, it comes out at EMR or wherever, and it makes the prediction and preferably then embedded within the EMR. Question 8, does the model actually then improve care and outcomes? So often, I think the first thing is to test models in pilot studies in a silent mode, just to make sure, okay, it produces a prediction, but we're not actually giving it to clinicians just yet, but we're allowing a panel of experts just to check, does this look right? You know, are there any errors in this or really implausible outputs? Then we perhaps may move into efficacy in clinical trials, and there's a number of perhaps methods that we can use. And in rapidly developing technologies such as machine learning, it may be difficult to subject every model to a randomized controlled trial. We may have to look at other designs such as before-after studies, interrupted time series, etc. But at the end of the day, we do want to look at large-scale effectiveness in routine clinical care and monitor how effective this model is over time. Importantly, the question is, could the model cause patient harm? And I think there's a couple of things here. One, that we need to understand that over time, there may be a shift in the underlying data set. In other words, the patient demographics, the disease epidemiology changes. We may also see what's called concept drift, where there's a change in clinical practice, a change in patient behavior that we now need to take into account. And even as we apply machine learning, it itself may change behavior, which then becomes the input data then for a new model that needs to be updated. Adversarial cyber attacks, I think, are a real concern because we know what hackers can do and they can really bring a system down. And there's been instances where even just slight perturbations in the data, for example, in an image, may cause the model then to produce a completely wrong diagnosis. Even though the clinician, when looking at it, perhaps may have taken that slight perturbation into account and still come up with the right diagnosis. So computer programs are very sensitive to cyber attacks, and people are now looking at how we can protect our systems from this. There's a concern that we may de-skill clinicians by using machine learning. Clinicians will then become over-reliant on machine learning and perhaps not pick up the occasional instance where it may be producing an abnormal result or incorrect result. And there's also some concern that overdiagnosis may be an issue where the sensitivity of machine learning may actually show up anomalies or abnormalities which really don't mean anything, but which then fire off a lot of false alerts. And then finally, question 10, does use of the model raise other ethical, legal, or social concerns? And we could talk about this for hours because again, there's, I think, a real challenge in many of these questions that when we actually look at the real world application of machine learning, we're going to have to confront. Again, we don't have time perhaps to go through those, but at least I'll list those as I think some of the important ones, and certainly some of the things that we've been looking at here within our own clinical AI working group. So in conclusion, I think, well, machine learning is here to stay. I don't think it's going to go away. It does have potential, and we need to engage in it. So for that reason, we need to have some understanding. We need to be beware of bias and inaccuracies in the training data in particular. And again, clinicians really are best placed to try to understand what is the data that's been inputted, have all the variables that I think are important as a clinician being included in this model, and where has that data come from and how good is it? Need to ensure that models are externally validated, that they've demonstrated clinical utility and safety, and they actually save time, and that they can be easily activated, interpretable, and as explainable as we can get them, but knowing that there may be a limit in what we can do there. I think the question is often asked, will AI replace physicians? Well, the answer is no, folks. You don't have to worry about your job. We will continue working as clinicians, but I think it's fair to say that some of our roles and some of what we do may change, and we're going to have a different mindset in relation to machine learning. And so I sort of think that AI and machine learning in particular isn't going to replace us, but those of us who use safe and effective applications perhaps may replace those who do not into the future. But let's talk about the future. And with that, I'll say thanks very much.
Thanks, Ian. That was a fantastic introduction. It certainly helped me understand machine learning better. I'll be seeking out your article on demystifying machine learning for sure. And I guess for me, it highlighted the importance for us as clinicians to embrace machine learning. As you said, it's here to stay. And you really highlighted the importance of the clinician engagement and helping ensure that models are relevant and going to have clinical application at the end of, rather than just using all this data for the sake of using data. I've certainly got a lot of questions piling up, and I would encourage others, if you've got questions, to use the Q&A on the right-hand side of your screen. But for now, we'll move on to Dr. Jonathan Chen. So Jonathan joins us from Stanford, where he's an assistant professor in the Department of Medicine, Centre for Biomedical Informatics Research and Division of Hospital Medicine. Jonathan leads a research group that seeks to empower individuals with the collective experience of the many, combining human and artificial intelligence approaches that will deliver better care than either can do alone. Jonathan, thank you so much for joining us today.
Fantastic. Thank you so much for having here. One of the perhaps surprising but nice side effects of our situation, we can't actually do this international conversation, which would be so hard otherwise. And so fantastic to hear from Professor Scott. It's just interesting how many fundamental concepts, that's exactly what I would have said. It's just, we can really kind of, I think, really mutually learn from each other and echo some principles, which may work just as well. In my medical school, one of the tenets we learned is you need to learn some things once, twice, and 3 times. That's how you make it stick. So we'll review some similar principles, but also some ideas of where to go with it. So thank you again. But going into it, I mean, what are we all here for anyway? What are we so excited about? Professor Scott gave a glorious review of all these principles, but why is it we're all so excited or so anticipatory anyway? I'll tell you what I think it is that we have this collective anticipation over the potential of such emerging technologies that are now able to automatically answer questions we previously would have thought it would be impossible for a computer to answer. Not long ago, this would seem impossible for a computer. You know, answering questions like, is that a Chihuahua or a blueberry muffin? A kitten or a caramel ice cream? Dog or bagel, or my personal favorite, parrot or guacamole? We now have algorithms that can automatically identify every cat video on the internet and fill your social media feed with the perfect clickbait to keep you distracted for hours, and while siphoning off your personal information and polarizing your political views, perhaps without you even realizing it. It does get you to wonder, though, perhaps there could be slightly more meaningful applications of such technology. Perhaps like one of those examples that Professor Scott referenced. Say, is that a picture of a benign mole? Or is that cancer? Is that melanoma? Is that a normal, healthy lung? Or is that infected pneumonia? More and more, you're going to see examples like these. That list that Professor Scott look is going to grow and grow of clinical questions that can now be answered with superhuman levels of accuracy by automated algorithms. And yet, medicine, healthcare historically and consistently lags behind other industries by over a decade in terms of our effective adoption of information technology and use of real-world data. Even though, I mean, shouldn't medicine, healthcare be the place where we should be doing this the best, the place where literally lives hang in the balance? Considered by some estimates in the US that medical error could be the third leading cause or contributor to death in the nation. Others argue this is completely flawed. This number is nonsense. Look at the prior studies. It's not 250,000. It's probably 100,000. Maybe it's 50,000. So a couple things. Even if we're only 50,000, that's still a jumbo jet airliner of patients being pushed over a cliff to the deaths. And more so, what's concerning is precise that we can't tell you what the number is. We don't know. Apparently, that is how much we care about reliably capturing and using our data in healthcare. But maybe lives are too abstract. Well, then, how about the money? This is US data, but this is really a worldwide challenge. That there's this fundamental challenge and tension with inefficiencies and waste. Estimates are that up to a third of the $3 trillion we spend on healthcare in the US alone is waste. It's administration, it's unnecessary services, prices that don't actually help anybody. Perhaps it is no wonder then that many are looking for emerging technology, intelligence systems, some way to help us make better use of our scarce healthcare resources so that we can do more good for more people. I mean, what are we even talking about anyway, though? I think back to my PhD in computer science a decade ago, AI, artificial intelligence, I assume we're talking about HAL 9000 or maybe Jarvis from Iron Man or something, right? Thinking machines that can reason through complex problems and adapt to new situations. We're nowhere close to such technology. I would shock me what's called AI nowadays. But if you really break it down, well, really what it is, it's a marketing buzzword. That's what it is. Professor Scott's the very same Venn diagram here. Well, if we go with a much more general definition, okay, AI is just any time a computer can kind of mimic intelligent behavior. But nowadays, when someone is selling you AI, almost always what they're actually selling you is machine learning, a set of tools and techniques to organize and make sense of complex data sources. Deep learning is a particular subset, largely rebranded neural networks, been around since the 1970s, but has in recent years been shown to be particularly effective at certain tasks like image recognition or speech recognition. The common thread here is this is as opposed to the way you would imagine programming a computer from the top down with the rules. Like here, I got a basic rules-based expert system. This is a great example of AI from the 1980s. Patient has fever and an elevated white blood cell count. I think they have sepsis. I predict they have sepsis, bad infection. Perfectly reasonable rule, have a computer execute that. That's AI right there. But instead, machine learning is, these are algorithms that learn by example. They learn by data from the bottom up. Like I got 100 patients here with sepsis, and I got 100 here who don't. What is it? Fever, white blood cell count, procalcitonin? I mean, I don't know. Computer, you just look at these and you tell me. You tell me what makes them different. That's the kind of approach that these systems work by. Learn by example, learn by data, rather than being programmed from the top down. Very similar hierarchy as Professor Scott shows. There are many different categories of machine learning technology and applications. Although again, most of the time, what you're being sold is something very narrow. Almost always, it usually ends up being a supervised learning classifier. And so just to reiterate, these are not thinking machines. These are models designed to answer very narrow multiple choice questions. Right? Look, is this a picture of a cat or is it a picture of a tumor? Is my patient going to have a stroke in the next year or are they not? Often framed around predicting which answer is most likely. So let's walk through a clinical example just to think through how such things could be useful in our clinical practice taking care of patients. Maybe your colleague or family friend is not feeling well. Ooh, shortness of breath, chest pain. Go to the emergency department. We take a look at them, get concerned, do a CT scan. Uh-oh, pulmonary embolism, blood clot in the lungs, bad news. But that's okay, it's a very dangerous situation, but you start the appropriate therapy, blood thinners, and that's like the right next step. But now imagine you as a human physician, you now have to make a prediction about the future to make an important decision. Is this patient going to be okay? Because I need to decide whether or not to bring him into the hospital or not. Right? So how would you do that as a human being? How would you do that? Right? You talk to the patient, you examine them. I would lay my healer's hands on them and feel it out. And you know what? This patient's going to be fine. everything's going to be okay. Just take the medicine, go home, everything will be fine. You can trust me. I'm a doctor. Now, as much as I like to joke about that, actually, expert intuition can be extremely effective and quite powerful. The challenge with it is that it is extremely difficult to reproduce, which means that it is essentially impossible to deliver it at scale with consistency without some kind of support systems. Support like, say, let's use our data. This is a mocked up example. Imagine every dot here represents some patient who had a pulmonary embolism. And we plotted them out in 2 dimensions based on their initial heart rate and their oxygen levels when they showed up in the emergency department. Blue dots were patients where they got better. Everything was fine. It was okay. Red dots, something bad happened. Maybe they had to get intubated, they're in intensive care, or maybe they died. The question for you then is, what would you do if Mr. Green showed up in your emergency department with a pulmonary embolism? Well, you could intuit it, you could feel it out, I think it's going to be okay. Or how about, let's draw a line through our data in a mathematically optimal way that puts as many blue patients this side and red patients that side. And now we can quantitatively support what we are already intuiting. Mr. Green looks a lot more like a blue patient than a red patient. I think it's going to be okay. Many different facets, but now what's shown here is 3 example input data in the top left, red and blue patients, and a battery of different machine learning algorithms, all trying to figure out how to separate the world into red and blue spaces. The broader point to make here is this is all standard tools now that have been around for decades. Open source software. Combine that with the increasing ubiquity of electronic health data and how the time is ripe for machine learning applications to be readily used in different healthcare settings in ways that just wasn't even possible. Just the infrastructure just didn't exist a decade or more ago. Before we go too far, though, realize these really aren't new concepts. It's nothing actually that new. Conceptually, this is things we've been doing in medicine for decades. If you didn't catch on the analogy I was describing, it was basically this pulmonary embolism severity index score. You can go on this website, they have hundreds of example risk scores have been calculated. And based on that, it estimates based on prior cohorts of patients, how likely someone is to have a bad outcome, use that to grade your decision making. In medicine, where we get CHADS 2, are you going to have a stroke? Decide if you need to anticoagulate. Apache, see if you're likely to die in the ICU. All of these things we use to grade how at risk somebody is, decide whether it's worth it to do certain interventions. Outside of medicine, these algorithms are pervasive and affecting your lives every single day. What's your credit score? But a prediction, will you repay your loans? Your email blocks out spam all the time using these algorithms, trying to guess what's spam versus what's a real legitimate message. What's different now is this potential for automated scores, right? This website on the left as an example, that's great, but oh, you got to open up another web page application. You got to data entry in all these numbers. You got to do it 1 patient at a time. Now with the electronic health record infrastructures, as clunky as they are, it makes it possible to, why study 5 pieces of data? Study 100 pieces of data about all your patients 24 hours a day. That becomes possible in a way that, again, just wasn't even feasible in before. Before we go too far, though, just beware of the difference between inference versus prediction. You're used to hearing observational research studies, coffee is associated with heart attacks. We change our mind. Actually, coffee now prevents heart attacks. It just goes back and forth. This is classic observational research, trying to find associations, right? It's trying to explain something about how the world works, right? Anybody think smoking is bad for you? Anybody think smoking causes lung cancer? How do we know that? Evidence-based medicine. There's no randomized control trial that proves that causation, but we have cohort studies. And adjusting for as many causal confounding factors we can think of, it still looks like that's an independently associated risk factor. That's something we can act on now. Contrast that to these prediction models. They don't know, they don't care how or why anything works. All they're trying to do is get the best possible prediction accuracy, because that's all we've told them to do. So just beware that a machine learning prediction model can easily learn things like patients who've been seen by palliative care are very likely to die, which is true. This is true. This statement is absolutely true. Please don't conclude, oh, well, let's just fire the chaplain and fire palliative care and that'll reduce patient mortality. Like obviously that is not correct, right? You immediately know that doesn't make sense, because confounding by indication. The kind of patients palliative care wanted to go see were the kind of patients who weren't going to do that well. But the hardest thing to train a computer is common sense. So being able to put that into context is something we always have to consider. Thinking more broadly, there's also many potential for data that's it's very hard to get label trained, especially in medicine. It's so expensive to hire doctors to label these cases. But what can you do with just the masses of data that are generated, right? In that comic, what do we do with all this big data we have? We don't know how to deal with it. It turns out there can be a lot of value in unsupervised learning. For example, in market basket crowdsourcing. What is this? If you ever go to your supermarket and you buy groceries and they'll give you free discounts and you can sign up for a club card, what are they doing that for? They're doing that so they can keep track of what you buy now and over time and figure out how to advertise to you better, basically. A classic story, one supermarket found that people buy beer and diapers together a lot more than you would expect by random chance. Not necessarily something you would have expected, but you can apply a theory to that data now and put all your diapers in the back of the store and then put your really expensive alcohol next to it. Maybe your beleaguered parents will pick some up on their way through. So I try to take this concept to medical decision making. So one of my key threads of work from my proprietary career development board, this is meant to be a mock-up. Pretend this is Epic or Cerner. This is electronic medical record interface. So doctors trying to take care of you in the hospital. And what it's showing is just a top 10 list, the most common laboratory test medications that a doctor orders at Stanford Hospital. If we knew nothing else of the patient, it just tells you this generic bestseller list. Here I'm going to type in CBC and do a manual search for a CBC with a complete blood cell count, just a regular type of order, standard functionality. But now what's happening here is the prototype is saying, hey, given that you've ordered a complete blood count with a slide check, these in the middle are the clinical orders that are most likely to occur within the next 24 hours. And the right are the ones that are disproportionately likely to occur within the next 24 hours. Like say, oh, actually, now that you mention it, oh yeah, I click reticulocyte, adds that to my shopping cart, as it were. That's a good one because I was worried about anemia in my patient. That's a good test to help me think about the next step. Now, given these two pieces of information, the system juggles a list again. It thinks maybe I might want a ferritin, a transferrin, and actually, you know what I wanted? I wanted a haptoglobin because I think this patient might have hemolysis. And then the system juggles a list again, and now LDH and direct Coombs test are starting to float to the top of the list because the system is starting to guess, basically. It's putting it together that maybe that's what I'm looking for, is working up a hemolytic anemia. The broader principle I'm trying to think about with this design is notice that at no time did I ever stop and data entry in the term anemia or hemolysis or type a note about it or pick an ICD-10 code. Look, I'm just taking care of my patient. Right? I'm just doing what I was going to do anyway, order the diagnostic test treatments, the stuff I was going to do anyway. But couldn't our computer systems pay attention to what we're doing and infer the relevant patient context and anticipate what we need before we even need to ask for it? I think that is very much possible because it's not like I'm the first person to work up hemolysis before. There have been thousands, tens of thousands of people have done it in even one institution. Can't we learn from their prior behavior to provide directed suggestions? How did I make this, by the way? Did I study the clinical practice guidelines, my textbook, and studiously program rules? If anemia, then recommend reticulocyte, if positive, then check. No, that's the 1980s approach to AI systems, and actually very powerful, very good for a useful system short term. But medicine keeps changing. It's hard to keep adapting to the constant shifting demands. Maybe I hired 100 doctors to manually label 100 anemia cases. What would you do in this case? And then I learned from that. No, I also didn't do that because I can't afford that, right? It's very laborious to do this manual labeling of data. But maybe we don't have to, because what are we as clinicians? We're like an army of manual annotators working every day, taking care of our patients, studying their information, and we're telling you through our orders, that's the concrete manifestation, our best guess of what the next best step is, the next diagnostic test or treatment is to make. That's a broad sense of some of that conceptual example, but if any ways this could go wrong, just because something is popular does not actually mean that it is good. Are we learning from the wisdom of the crowd, or are we suffering the madness, the tyranny of the mob? Really hard to unpack because there is no gold standard to define what good medical decision making is. I would encourage you to read my research papers. I dived into this is a very deep, complex topic, but just as an anecdotal example to conceptualize why this surprisingly may work better than you might expect. So remember, TV game show, Who Wants to Be a Millionaire? Answer multiple choice questions for big money. A classic thing on this show. If you didn't know the answer, you can call a lifeline, phone a friend. What does that mean? You can call anybody in the world you want. I would call the smartest, most knowledgeable expert I know. I would consult a specialist. Or you can take a poll of the studio audience. This is a knowledgeable experts. It's just regular people watch a TV game show. How well do these two approaches work? Turns out if you phone a friend, they'll be right 65% of the time. It's way better than random. Turns out the audience is right over 90% of the time. What on earth is going on? It doesn't mean they're geniuses. They all pick the right answer. In this case, only 55% pick the right answer. It turns out as long as the audience vote, the voters in your jury, in your democracy are just better than random, then in theory, you can aggregate the votes of many voters and create a strong classifier from many weak classifiers. This is why we have juries and democracies and not dictators. And also, if you like machine learning, this is why ensemble machine learning approaches where combining the results of many can be surprisingly powerful when you put it together. Even though there are many who get it wrong, as long as people get it right more often than wrong, there's a lot you can learn from it, this amplification effect. Any other concerns though? Other people say, hang on. I built this recommender system, this kind of like shopping recommender, but for medical decision-making. Isn't that gonna lead to overutilization? A commercial website, they recommend you products. They just want you to buy more stuff. They don't really care if you're happier, right? This is a real phenomenon. You gotta figure out the counterbalance here. Because there is this fundamental tension between quality, cost, and access. You cannot make all three things better in medicine because of that fundamental scarce resource. One of the scarcer resources is access to that specialty, is access to the knowledge of a competent expert. I would like to see 20 patients tomorrow. You need more? I'll try to see 30 tomorrow then. You want me to see 40 tomorrow? Like, I'll try, but at some point, I just physically can't anymore and provide safe care. So this is why a lot of political dogfights are on medical insurance and distributions, right? How do you do that? It's always a trade-off. You help in one direction, you broke something on the other side, almost certainly. My naively optimistic approach is the only way you can break out of this cycle is one, you create supply by, say, automation, AI systems, or you systematically identify and eliminate fraud, waste, and abuse, inefficiencies. And again, back to the example, so the specific paper being referenced, I try to look at laboratory diagnostic tests. Tests represent over 200 billion years in the US alone. It's the high emphasis volume medical procedure. And estimates are in the hospital setting, up to a quarter to half of the lab tests we order are unnecessary. They don't actually help the patient. It's just stuff that keeps us busy. It's just an interesting daily test to look at so our interns and medical students can look at them, but really isn't improving patient care in any meaningful way. So here's the really foundational concept of how we try to design this research project, was the utilizing the threshold approach to medical decision-making. This is a concept established many decades ago. If you look at the gray bar from 0 to 100%, we're really trying to estimate the pre-test probability of something. Pretend that's the probability you believe a patient has a diagnosis or that their lab test is going to show you an abnormality that's interesting. If it's really close to 0%, like, why bother ordering the test? It's so unlikely. It's just not worth it. Just move on. It's not likely to happen. On the other extreme, if it's close to 100%, again, why do you bother ordering the test? It's so likely to show you that finding. Just start treatment. Just act as if. It is really only in the middle area of uncertainty where testing is useful, so you can push yourself past either the threshold to test or the threshold to treat. So let's build this up in successive layers of complexity. Start simple. Here are the most commonly ordered and repeated laboratory tests at Stanford Hospital. So everybody gets a basic metabolic panel, and that total bar represents the total volume per number of encounters. The black part of that bar represents the number of those tests which are a repeat of the exact same test within 24 hours. Well, a metabolic panel, your chemistry test, well, maybe I need to check that a couple times a day. I'm diuresing my patient, I'm going to check their potassium level. Maybe. Okay, that could be plausible. How about a complete blood cell count with a white cell count differential? How about a phosphorus level? Do you really need to check that every day, let alone multiple times a day? No, the answer is no. There's like no clinical reason where that would really be justifiable. It's just these habits we develop. Further examples you can find based on guidelines for many common tests, again, repeatedly ordered within 24 hours a day, hundreds if not thousands of times per year just at our one hospital, including things like the patient's albumin level, their hemoglobin A1C. It is not even biologically plausible that these numbers could change that fast. so there's really no justification here that this is just a mistake. This is just waste. There's no reason to do that. Let's get a little bit more nuanced. How about repeat testing? So this is how likely a test is going to give you a normal result based on how many times you've repeatedly checked it and it showed a normal result. Let's look at the purple curve, your hemoglobin, your blood concentration. If it's your first test, so 0 repeats, actually most people in the hospital, they're sick for some reason. Only 10% have a normal hemoglobin the first time you check. But after you've had 1, 2, 3, 4, 5 repeats in a row and they've all been normal, it's not 10% anymore. It's rapidly approaching 100% that it's still going to be normal. You've already seen 5 normals in a row. You're getting rapidly diminishing returns on the value of information of this repeated diagnostic testing, given what you've seen so far on the prior results. But that's just repeats. That's just numbers. What if we could use so much more context about our patients? Right? What if it's not just their prior repeat? What if I know their age, their comorbidities, their other labs, their vital signs, all the things we already have in the electronic medical record, pour all of that into the pile of linear algebra, I'm just going to call machine learning right now, stir the pot, and then see, can you predict the results of diagnostic laboratory tests even before you've ordered them based on all the information that's already available about the patient up to that point? If you could, you can start to empirically estimate these pretest probabilities, and then doctors, I think, will know what to do with it. It's very like doctors have the right intuition, but it's very hard just for humans to do that quantitative thinking. So that's kind of thing, as Dr. Scott pointed, let the computer do that part. I'm going to zoom in on just the results here again. Look at the paper. We did this on multiple sites. There's multiple decision thresholds to think about. But I want to kind of hone in on just some of the key example results. We zoomed in on we wanted a 95% negative predictive value when we chose our threshold. And what's shown here is, again, some of the most common laboratory tests ordered at Stanford Hospital. And the total bar represents the total volume, how much we do all the time. Everything to the right of that midline are cases where the algorithm could have predicted this looks like it's going to be a normal result. You haven't even ordered the test yet, but I'm pretty sure, 95% sure it's going to be normal. And indeed, the green is how often we are right. And the red sliver is how often we are wrong. But what that implies is all the green is suggesting for a lot of these diagnostic testing, we're ordering a lot of them, even though it's not being normal isn't the problem. It's when it's predictably normal. Then why do you even need to do the test? You could have guessed, you could have predicted so easily what the result was. You really didn't gain much information suggesting an opportunity to eliminate that inefficiency. And we have active implementation efforts going on right now, specifically targeting magnesium and phosphorus, given that those are the most prevalent ones in our inpatient setting. Let's start to wrap up in terms of a key conceptual thinking. You might think it's like, hang on a second. Just because something is low information does not mean it's low importance, right? There can be extreme imbalance between risk and benefit. False positives may hurt a lot less than false negatives, right? What if there's these rare events? Medicine is plagued with these issues where there's a really unlikely thing. You don't even want to think about it, but if you miss it, it is catastrophically bad, right? It never hurts to get more information. Come on, just order the test. Just order the test. This doesn't hurt, right? You know, this is how like cancer screening works, right? The vast majority, 99% of people get no benefit from it, but you're just trying to catch that one person whose life you'll save. Let's think about this, blood culture bottles. If you're worried somebody has bacteremia, blood sepsis infection, you can't miss that, right? That's very serious. So you order a blood culture bottle. You don't actually care what the blood culture test shows. What you care about is, does your patient have a blood infection or not? And that test itself is only correlated. It is only predictive of that patient state that you care about. And it is an imperfectly sensitive test. Thus, we don't order one blood culture bottle. The routine standard of care is you order 4 blood culture bottles because you want to increase your sensitivity, your chance of catching that very bad thing you don't want to miss. So here's a question. Why do we stop at 4 blood culture bottles? Why don't we check 5? Why don't we check 6? Why don't we check 12? Right? I mean, if we worry about infectious endocarditis, a heart infection, that's really bad. You don't want to miss that. The routine standard of care is you order 12 blood culture bottles over the course of a day. Why stop there? Why not order 50 blood culture bottles? Just to really be sure. The more systematic umbrella foundational point I'm trying to convey is the reason you don't order the 50th blood culture bottle, because given the results of the last 49, the results of the 50th one are so predictable. Even though there's a non-zero chance that 50th bottle will tell you new information, it's so unlikely, it's so predictable what the result will be given the past 49, it's just not worth it anymore. The value of information becomes so low that it's not worth doing. And repeat is something easy to understand, but I think given all the context about our patients, that's what we do as physicians all the time. You're always adjusting your Bayesian probability of a diagnosis to know what things are worth pursuing and which ones are not worth. So I work with the final thoughts about the potential machine learning, AI concepts in medicine and healthcare. I wrote this perspective a few years ago because I was getting worried. This is the Gartner hype cycle for emerging technology. X-axis is time, and y-axis is expectations, hype. It's how excited we are about new emerging technology. I got worried because I know what was at the tip top of the peak of inflated expectations. It's deep learning, machine learning, and so-called AI technologies. I got worried because I know what's going to happen next. We're going to crash into the trough of disillusionment. You can see blockchain's already headed down because people will be disillusioned. People will wait. I heard 80% of doctors are going to be replaced by algorithms. I thought we poured all this data in the computer. Out would come the cure for cancer. Like, why is this not happening? Like, stakeholders are going to pull their support. Public is going to lose trust. It's like, hang on a second. I'm not sure those are the right expectations to have. That's why I've really enjoyed having these kind of conversation discussions. Learned a lot from Professor Scott. He had a great overview of all these principles. So I think that helps us foster a better appreciation for the capabilities, the limitations, and the implications of such emerging technology so that we can soften that crash and quickly move on to the slope of enlightenment, where we effectively use all of our information data sources to best improve our collective health. I'd like to leave the last comment about that, common questions like, is our computers going to be smarter than humans? No, humans will always be smarter than computers. A very interesting intellectual debate we have about that. Be a lot of fun. And I actually think it also doesn't matter because it's the wrong question to ask, because the answer is, let's combine the best machine learning software with the best human clinical hardware, and together we're going to deliver better care than either of us would alone. Thank you, everybody, and happy to pass it back to Dr. Lawrence for discussion.
Thanks, Jonathan. That was another excellent presentation. I really liked your summary. Feeling quite reassured by both speakers today that we're not imminently about to be replaced by machine learning, but that it could be a powerful tool. And Jonathan, you covered in your paper discusses in more detail the use of machine learning to reduce lab tests. And I guess we started here with the premise that we're talking about low value care and that we know up to a third of the care that we order is unnecessary or wasteful. So, using the information known about the patient prior to the test to be able to improve that pre-test probability does seem like a powerful way to improve the value of the care we provide. So you've both certainly helped machine learning become a little bit less mystic now, but how close do you think we are? Are we at the point where it's about to be rapidly adopted and translated into clinical practice, or are we still a little bit away from that yet?
I'm sure Professor Scott will have some good comments as well. I think it's also this weird thing, it's kind of moving under your feet, because like I said, anybody use the PESI score? Anybody do CHADS2? Anybody use ASCVD to decide whether you prescribe cluster? And sometimes you already are using machine learning. These are prediction models, essentially, that drive our care. Anybody use an automated complete blood count differential in your laboratory? You almost certainly do. I'm not looking at the slide every day to count neutrophils. In some sense, we already are, if you want to count it that way. In terms of the ones that we're talking about today, the automated ones that are readily integrated and embedded, a lot of the infrastructure still needs to catch up to really do it at scale, but the prototypes at least are emerging now that I think we're only going to see more and more going forward. I'm interested to see what Dr. Scott has to say.
Yeah, no, I agree. I agree with John. I think it's just that, it's the time and the cumbersome nature of many of the rules that we have now. And we can, many of our registrars, they've got the MD Calc app on their mobile phone, and they'll open them up and they will use them. But the more variables you have to put in and the more you have to calculate and the more cumbersome it becomes, then they just don't do it. They say, no, I think I can make an intuitive decision that's probably pretty close to the truth anyway, and I'll just go ahead. So that's why I think at the end of the day, any model that we want to use, it's just got to be automated and self-activated. So it just happens, within seconds. In other words, it beats the human mind in that sense, provided that we're all happy that the prediction is accurate. So I think that's where we need to get to.
Yeah, and following on from that, I guess, you mentioned the risk of amplifying bias. And I guess in low value care, certainly what I see all around me is we're influenced by what others are doing. So, you know, if we're using the supervised machine learning to develop these machine algorithms, how do we avoid that risk of just amplifying more low value care, which is the opposite of what we want to achieve?
It's,
Well, I think,
go ahead. I'll follow
no,
up.
you go ahead, John.
It's challenging. I have a whole other line of talk to kind of describe that, where I say machine learning, basically it has, what it is it an amplifier. It has an amplifying effect. And whatever, it'll help you do whatever it is you are already doing, it'll make you better at that. And so one of the things we're doing is making good medical diagnoses more often than not and applying good treatments. These recommender systems, for example, that really could help supervise my learning, right? I'm learning from a supervisor, I'm learning from human experts. Let me be more like you. That could really be a good thing. But if one of the things we're perhaps doing is providing inequitable healthcare and, you know, practicing unconscious biases, it will probably make us better in terms of doing more of that as well, unless we specifically pay attention to that. So on the one hand, does that mean I'm a critic, like, oh, machine learning is terrible, it's going to make everything worse? I think overall it's going to make everything better on average, but we have to be aware of this, and it can still be a valuable tool, because often what it will do is it will make plain your unconscious biases, right? The tool didn't make us biased, it's revealing it in a very amplified way, and then we could address it in ways that maybe was too hidden before, was what I might think.
Yeah, no, I agree. I think that it comes down to just clinicians asking, what are we putting into this model? Okay, and if we're sort of encoding our practices because we think that's a good way to do things, then okay, the model will just say, okay, that's good, I'll learn that, and away we go. I mean, I think an example just to highlight is that you know, IBM Watson Oncology proved a bit of a disaster at Sloan Kettering, because it was trained on a certain strata of the American population. It was trained on the way that the oncologists within that institution actually practiced their oncology, okay, and it was trained on the outcomes that they were most interested in. And then when they tried to then apply it to a different population, it failed miserably. And you wouldn't use it because it was actually inaccurate. It was actually producing harmful predictions in other populations outside of that particular strata. So yeah, it comes down to, again, you just got to be careful and to say, well, is this model generalizable? Can I take it into other populations where there may be differences, as I said, in the demographics, in the standards of care, in the protocols, and how we actually measure things? So they're the things we just got to be careful about, because you're right, then we could amplify bias and error at scale.
Thank you both. And Ian, you mentioned that in Australia, we're lagging behind the rest of the world in terms of our TGA approved apps, the machine learning apps. How do we address that? And are they in mainstream care elsewhere?
It's fair to say that no, from what I can see, and perhaps John can correct me if I'm wrong, but I haven't seen yet anywhere in any sort of OECD or, you know, Western country where machine learning really has become mainstream. I mean, I'm sure that there are certain apps that are being used, certain prediction models are being used, I'm sure, in certain instances, but I can't say it's become mainstream practice as yet. And I think it's because the infrastructure perhaps hasn't caught up. I think that's probably our biggest concern. We still don't really have the ability to assemble and aggregate data and clean it and do all those things that we need to do, you know, in the pipeline. But I think also it's just that we need to integrate these models with the systems, with the electronic systems, the electronic medical records that we're currently using, okay, because that is the platform on which we're going to mount these models. So I think, you know, there's some major challenges here, as John and I were talking about before we came on, and I think it's going to take probably at least another 5 years or more before we really sort of, I think, overcome those issues. But I think we have the potential. I think there's certainly more potential now than there was 5 or 10 years ago. So I think we just got to sort of persevere, but don't sort of get carried away with expectations. I think, you know, we just got to take it course by course and make sure at the end of the day that these models actually do work.
Crystals, I was just making me think of other things. Is it really that much different? Or it's, you know, think about another new laboratory test or a new kind of MRI scanner or something, right? It's also like, why hasn't that taken? It's a new tool we have to learn kind of how to use. And just like your lab test, is a procalcitonin to tell you if somebody's infected or not? It's like, no, it doesn't tell you anything. It's just information that has a sensitivity and has a specificity. And as a clinician, we have to learn how to integrate that information. And if we have those expectations of these types of tools, it'll make them more tractable versus like, it's the bot that just tells us what to do. I think that's what's going to get us into trouble some big. I think the point is certainly about the infrastructure catching up. I think it'll get there, but it's taken some time. We're already far more advanced now than we were 5-10 years ago, anticipating those changes. I've worked with Abraham Verghese here at Stanford, who writes a lot about the trauma of the electronic medical record being imposed upon the medical establishment. I just grew up with it mostly. I have paper records when I was in medical school, but that most doctors, I don't know how it is in Australia, complain very much, especially in the US, because of also documentation billing requirements. And, oh my God, this computer is supposed to help me. No, I feel like all I do is data entry. That's all I do is I hash out notes and do data entry. There's this terrible thing. I want to spend time at the bedside with the patient. Instead, I sit at the computer doing data entry. And one of his principles he's putting forth, maybe the infrastructure AI is not coming for 5 to 10 years, but we better get clinicians engaged in that process, or don't be surprised when you get run over by it. And then, like the technical group just imposes and drops it in front of you, and now you're stuck living with it, when hopefully we can all be a part of designing it the way we want it to be. So it's improving our patients' care.
And that segues me nicely into my next question. And I guess, you're right, the new generation of doctors coming through have only ever known the EMR and that way of working and documenting. And I suspect that machine learning is going to be the next sort of frontier, and the newer generation of the next generation, that'll be their thing. But we've also talked about how it's really important to ensure that the role of the clinician in machine learning and getting clinicians engaged. So how do we best increase the literacy in terms of machine learning and AI amongst our clinicians and our patients for that matter? Perhaps I'll start with you, Jonathan.
Sure, it's tricky. These may be very controversial perspectives, so let's throw it out there and see how everybody feels, I guess. Of course, the easy answer is like, well, we need more education, right? It's like, well, the thing is, I don't want to be in medical school forever either, right? So if you want to put something in education, you got to take something out. So what's going to go out, right? Some would argue, I'm just describing what those potential be. It's like, memorizing the Krebs cycle, I totally did that, and I could have recited to every single enzyme. I don't really use that at all to treat my patients, but understanding sensitivity, specificity, evidence, Bayesian thinking, I use that all the time in terms of treating patients, even without machine learning, and even more so is that becoming more plain. A lot of these concepts that we're talking about, like, well, you have to understand machine learning. Well, technically, you already need to understand how observational cohort studies do. You have to understand randomized control trials, generalizability. Do the inclusion criteria match your patients? Do they match the settings that you intended? These are things that actually all of us are already supposed to think about. It's just another tool that's amplifying that in another way. So education broadly is the answer. I'm trying to make that more specific and concrete. I hope Dr. Scott's got the plan for us.
Yeah, no, it's a good question. And we're actually, I'm involved actually in redesigning the medical course here at the University of Queensland. So we're putting out a new course hopefully in 3 years' time. So we're having these discussions right now. And it is, okay, what's going to go out? Because, we can't go 6 or 7 years. In fact, we're reducing to 4 years. So yeah, it's a real tension. I mean, I think that there's, to me, that sort of rote learning that John and I were both subjected to in our medical student years needs to go by the board, because it's going to be outdated within the next couple of years anyway. All right, so there's no point trying to learn it, and it doesn't have immediate clinical application. Whereas really what I think we haven't taught very well is the reasoning skills, ability to actually think about the maths, about things like sensitivity, specificity, predictive value, for example, understanding data science, understanding machine learning. These things, these are concepts we do have to, I think, learn. I understand, because that's the way things are traveling. So I think the sort of the basic or the static knowledge to some extent has to go. Now I know that for some traditionalists, they're going to find that abhorrent. The surgeons will want their anatomy taught, the histologists will want their histology taught, etc. But we need to realize that, look, at the end of the day, for example, machine learning is affecting surgery, robotics is affecting surgery. We may have machine learning that will outdo the histopathologist in 5 years for many things. So what's the point then of learning the histology? We better learn more about, okay, how does machine learning help us make these sort of decisions and inform our decision making? That's probably the most important thing. So yeah, it's going to be a tension. So I'll report back in 3 years' time and see how we've gone, and hopefully not too many knives in my back.
Well, in a similar theme then, we know that medicine is evolving, and we've all got used to that concept that we're not going to be able to stay up to date with everything, and that what we learned in med school is now no longer true or relevant anymore. But, you know, in my experience, nowhere are things evolving more rapidly than in the world of technology, and particularly COVID saw a massive expansion in terms of the way we were embracing technology in healthcare, and, you know, machine learning is the step beyond that again. So if technology is evolving so rapidly, how do we keep abreast of the changes, and how will we monitor and update them over time? And this time I'll start with you, Ian.
Yeah, well, good question. I'm not so sure that I have the solution. Hopefully John might have, but I think we're going to have to, I think, you know, at the end of the day, our world is changing, and we're facing many challenges, and perhaps machine learning is a challenge for healthcare, but, you know, that we've got other challenges too. I think global warming is a pretty major challenge. And in that, we're going to have a pretty major reset in how we look at things, and, you know, what we think are effective systems, and what are the outcomes that we're most interested in. What are the values also that we cherish need to be taken into account. I think in terms of sort of life cycle monitoring of machine learning, well, the good news is that the software vendors that actually sell us a lot of the machine learning tools are aware of this, and they're saying, righto, well, we can also use our tools to look at, for example, are there data set shifts occurring within the input data? You know, are populations changing? We need to perhaps indicate at this time, it's perhaps now we need to retrain this model because things have changed to a point where we now are losing confidence in the accuracy of the model. So machine learning itself can be used as a tool to monitor itself and tell us when we think, okay, now that the time has come now to update, to retrain, or perhaps in some cases, time to abandon this model, and because we've got something that perhaps may even work even better. So I think perhaps that gives us some reassurance that there is a monitoring system built in. Okay, it's not just totally reliant on us as human beings, but at the same time, we don't want to, I think, also absolve ourselves of also continuing to monitor and make sure that this model is working as well as we think it is.
Yeah, it's a lot of challenging dynamics. I'll just throw some more of the provocative ideas just to get people thinking about it. I like my wife. My wife is a pathologist here, and so a couple years they had it was like, oh my goodness, are all these image recognition systems going to put us all out of business? Are we going to lose our jobs? It's like, no, it's not. But on the flip side, look, if you took a pathologist from 50 years ago and you just transported them in time and today, and you had them practice the way they fit you would fire them, right? Because it's not because of AI, it's just like technologists, though, the way like medicine is practiced doesn't stay the same. It never has. So no, AI is not going to replace your job, but like tools are changing. It's just another tool that we have to adapt and learn to. I really like some of Dr. Scott's principles where, you know, we have to teach our students how to learn, not teach them facts, because the facts are going to evolve, or it's going to be so overwhelming anyhow. And I think we kind of already have some of that culture, right? Like, how many people still memorize the physician's desk reference? Or how many people memorize every medication dose and let alone the list of medication prescribed? Now, I don't know what reference you guys, everyone just looks everything up and up to date, and that's a very powerful tool. So it's you move the database of information into a computer assisted form, so you can do the clinical reasoning, the counseling, all the stuff that really computers are really bad at, that humans are actually very good at. So I think that's a good kind of dynamic to figure out how to just change the role and responsibilities for certain parts of it. Let the computers do the thing that the computers are good at, so the humans can do the stuff that only the humans can.
Yeah, great. I like that. And then, you know, another fact you shared, Ian, that was quite surprising to me was 87% of these models are failing in real world applications. So can we get better at identifying which of these are likely to succeed?
Well, I think when people have looked at the applications, I think probably what comes out to me, certainly in healthcare, is that it just didn't have enough clinician input at the very beginning. Okay, so, you know, the task wasn't well defined. Okay, you know, the variables that needed to go into that model weren't well defined. Just to give an example, I mean, we were talking recently with one of our software vendors, and he was telling me this beautiful model in terms of predicting readmission, right? Because that's a common question that we ask: how likely is this patient to come back in? And, you know, showing me all the features, and it sounded all great and everything. But I said to him, hang on, one of the features that you haven't got is that length of stay of the previous admission, because I know from a clinician, the longer you stay in hospital the first time, the more likely you're going to come back. And he replied, but I'm not a clinician, I'm a data scientist. And I thought, yep, that's exactly right. So I think we need to make sure then that, so that application would have failed. okay, because it didn't have a key variable that I knew intuitively as a clinician. That was important to include. And most, traditional regression models for readmission would include length of stay. So I think it just comes to, again, why they fail, I think, is that, they haven't been properly designed and with the end user in mind. And therefore, that's why we, as sort of domain experts, clinical experts, we need to collaborate with our data scientists. So they need to learn our language and the way we think, and we need to also learn how they do things. And that's why it's important to come together. And that's why in our clinical AI working group here, we have a very close integrated collaboration between data scientists, computer scientists, clinicians, okay, and IT and informatics persons. And that's why I think we're getting a model now, for example, in relation to heparin dosing, that looks pretty good.
Fantastic. Many different people. I mean, so I was a software engineer before I came back to medical school, and I did my PhD in computer science. And it's, as an engineer, it's very fun to like engineer problems. Basically, it's very fun to build cool technology. And then anybody want to use this now? Right? So you try to push technology on people instead of probably it should be more like, why don't you find people who have the right problem? They'll pull in what they want, basically. So I'm trying to find out how do I pull in what's needed rather than try to push stuff on people that maybe they didn't actually need or didn't want, because there's all this context, there's implementation, there's workflow. Actually, there's a lot of incentives. A lot of things is a great idea and really probably would help patients, but the incentives aren't there. There's no business model you can make to actually sustain it, in which case it's hard to do anything to sustain it. A lot of the foundational ones, let alone the workflow and the data structures, it's just the basic problem construction isn't really that well conceived. At least some heuristics that I came up with to kind of help me think through them is the problem actionable, arbitrary, and ascertainable? I spent a lot of time thinking about illiterism. I hope you appreciate it. So one is it has to be actionable. It has to be something you can do about it. It has to be some important decision a human has to make. Admit to hospital or not, start blood thinners or not, or go to the ICU or not. And then it has to currently be arbitrary. There's a viable decision that's actionable, and it has to be variable. Right now, that decision depends on a human's ability to predict the future. Is this patient going to die in the next day or not? Are they going to have a stroke in the next year or are they not, right? Are they going to is their blood culture going to be positive or not? A human has to make this variable prediction. That means inevitably you have variability, inconsistency within, let alone across people, compromises your quality and efficiency. The other key feature is that it has to be ascertainable. Eventually, there does have to be a correct answer to the question. Like I could predict all sorts of things. Could you predict if I prescribe some opioids, some morphine to my patients, maybe they'll just sell it on the street. Maybe if you could predict that, that'd be great, and I'll know how to change my prescriptions. But how could you ever find out if your prediction is correct? There'd be no way to ascertain, to verify whether your prediction is correct. Without that, you can't really train these systems. But if you have an actual thing you can actually do about it, it is arbitrary. That means you can improve it with consistency, and you can verify the correct answer. Or that at least are the basic ingredients for a problem that it might be able to be assisted with these types of technology.
Thank you both. I think, it's been a fascinating hour and a half, and unfortunately we are coming to the end of that now. I think this is an exciting time, and, potentially there's been a lot of significant transformations over the last, along the history of medicine, but this is certainly one of them. And I think we've got a great opportunity now to think about how we use machine learning and medicine to our advantage and to improve the value of care that we provide. So thank you both very much. And I would like to thank all of those who have joined us or are listening to this online. It's been a great conversation. Thank you.
Thank you to those that have joined us today. That concludes today's session.